Hello everyone, I'm Shalini, student of SVCE. In this video, we will explore the fascinating world of probabilistic modeling, which is joint probability distribution and Markov chain. Here we have the contents: joint probability distribution introduction, properties of joint probability distribution, marginal probability distribution, conditional probability distribution, independence of random variables, joint probability distribution examples, applications of joint probability distribution, Markov chain introduction, applications of Markov chain, comparison between joint probability distribution and Markov chain, conclusion and summary. Starting with the introduction of joint probability distribution. Definition: a joint probability distribution describes the likelihood of multiple events occurring together. It assigns probabilities to all possible combinations of events. Multiple dimensions: the joint probability distribution of two random variables x and y with discrete probability mass functions can be described with a two-dimensional table. Pairs of events: it gives the probability for every pair of events from x and y. Two variables: a joint probability distribution is a probability distribution that describes the random variables x and y simultaneously. Characteristics: they provide insights into dependencies and correlations among variables, enabling data-driven decision making. Properties of joint probability distribution: non-negative values: the probability of every event is always greater than or equal to 0. Mutual exclusivity: the probability of the joint occurrence of two non-mutual exclusive events is equal to the sum of their individual probabilities and the probability of their intersection. Total probability: the sum of probabilities of all possible events is equals to 1. Marginal probability distribution, X marginalization. The X marginal probability distribution gives the probability mass function of X. Y marginalization, the Y marginal probability distribution gives the probability mass function of Y. Marginal independence: if X and Y are independent random variables, then their joint probability distribution is a product of their marginal probability distributions. Next, we have conditional probability distribution. Definition: it describes the probability of one event given that another event has occurred. Formula: P of capital X is equals to X or capital Y is equals to Y is equals to P of capital X is equals to X, comma, capital Y equals to Y divided by P of capital Y is equals to Y. Bayes theorem: the formula for updating probabilities based on new data. Examples: one example of conditional probability is estimating the probability of a student passing a test given their class attendance. Next, we have independence of random variables. Coin tossing example: two coin tosses are independent events. The probability of getting tail on both tosses is 1 by 4. Weather forecast example: the weather today is independent of the weather tomorrow. The probability of tomorrow being sunny is the same regardless of today's weather. Dice rolling example: when rolling two dice, getting a 5 on one die is independent of getting a 4 on other. Next, we have a table of joint probability distribution, which gives an example of a 2D joint probability distribution between two binary random variables x and y. Here x starts from 0 and ends at 2 and y starts from 0 and ends at 2, where p of 0, 0 is 0 0.05 and p of 0, 1 is 0 0.1, and it goes on. Next, we have applications of joint probability distributions. Machine learning: joint probability distributions are used to model multivariate data, hiding in tasks like pattern recognition and anomaly detection. Financial risk analysis: by modeling the joint probabilities of market variables, we can assess risk, construct portfolios, and optimize investment strategies. Genetics: joint probability distributions help unravel the complexities of genetic inheritance and the interactions between genes. By the by, we have Markov chain introduction, definition and concept. understand the fundamental principles and concepts behind Markov chains, including states transition and the Markov properties and components. Discover the key properties and components of Markov chains such as transition probabilities, state space, and stationary distribution. Markov chain models in various fields. Explore real-world examples of Markov chain models used in diverse fields, including finance, biology, and social science. Next, we have applications of Markov chain. Urban planning. Learn how Markov chains help in urban planning by predicting population growth, traffic patterns, and land use changes. Machine learning. Discover how Markov chains are applied in machine learning algorithms such as hidden Markov models for speech recognition, genetics, and evolution. Explore how Markov chains aid in modeling genetic mutations, population dynamics, and evolutionary processes. Climate modeling. By simulating the transitions between weather states, Markov chains contribute to climate modeling, aiding in weather forecasting and climate change analysis. Text generation. Markov chains can generate realistic text by modeling the probabilities of word sequences, making them invaluable for chatbots and language models. Queuing systems. Markov chains help analyze the performance of queuing systems, optimize resource allocation, and improving customer satisfaction. We do have some limitations and assumptions of Markov chain, which is non-memoryless assumption, finite state space, and stationary distribution. Next, we have the comparison between joint probability distributions and Markov chains. In joint probability distribution, model probabilities of multiple events occur together, whereas in Markov chains, model sequences of events occur with dependencies. Joint probability distribution provide insights into relationships between variables, whereas Markov chains focus on probability of transitioning between states. Joint probability distributions are widely used in statistical analysis and machine learning, whereas Markov chains are used in time series data and dynamic systems. Concluding the topic by summarizing the prior slides. Foundation of probability theory. Joint probability distribution is a cornerstone of probability theory and allows us to understand the relationship between two random variables. Useful tool for decision making. It can help determine the probability of a particular event occurring based on the relationship between the two variables involved. Summarize the key takeaways from the presentation on Markov chains and discuss avenues for further research such as applying Markov chains to emerging technologies or refining existing models. Thank you.